Okay, so we're going to start looking at module number 3, which is velocity analysis. We're going to go to chapter 6 in our book now, okay? And that's where the velocity analysis section is. And also you'll notice that when we go into the learning plan portion here, I do have a PowerPoint presentation, which is going to be what we're going to be focusing on this evening, which is part 1, if you would, of looking at velocities, which is chapter 6. So I'll kind of get this going in the background. Additionally, I have the handout there, and I have that, here underneath my camera. So we'll reference that as that comes up. So chapter 6, velocity analysis. This is going to be starting on page 123 in your book. So if you did want to open up, we'll be referencing that as we go along. So objectives of this chapter. First of all, we're going to be dealing with all different types of velocity. And the 2 main types are going to be linear and rotational. And then additionally, we're going to be finding out what relative velocities are. And then we're going to be converting between linear and angular velocities, as well as different unit types. And then we're going to be applying the relative velocity method to graphically solve for the velocity of a point on a link, knowing another velocity on a different link. So we're going to be using these 4-bar mechanisms that we've been looking at in the first 2 modules, and we're going to be now kind of looking at individual points and how fast they're going. Okay, remember, kinematics is all about spatial relationships or displacements, and then also motion, velocities, acceleration. It is not worried about forces. Okay, so we're not doing any type of force analysis here. Then we're going to be using that relative velocity method to also graphically solve for velocities that are points of interest or on floating links. Okay, so we'll be kind of learning about that as well. So first of all, in this chapter, our biggest objective here is to determine how fast certain points are moving on a linkage. Okay, and as we move around about linkages, just kind of by the nature of the 4-bar mechanisms we are looking at, most often at that driver level, like at the driver on our 4-bar mechanism, we're probably going to know most about that. Meaning a lot of times that driver is going to be connected to a motor. So we know how fast that motor is going. And then we know usually what the lengths of the links are, which is going to help us to find velocities of points. But then it's really going to be, once we know what's going on here, what's happening on our output, because it's all dependent on what's going on here. Okay, so that's where this velocity analysis is gonna kind of work from what do we know about, so that we can figure out what is our unknowns over here. And that's where we're going to use those relative velocity methods to work through the different links to get to that output. Now, linear velocity. Linear velocity should be quite familiar to you. I believe everybody has had physics before they've gotten into here. So linear velocity is going to be that straight line displacement of a point per unit of time. So the basic equation for velocity is going to be how much distance do we cover and how much time did it take me to cover that distance. Okay, so distance divided by time. Now in this book, I'm not exactly sure, but they use the variable capital R for distance. Many times we'll see it as D, lowercase d, and that's what I use most often. It's also not uncommon to see it as S. Okay, is there something like computer wise?
I'm taking notes.
Oh, you are? Okay, all right, sorry.
No.
No, it's not that. I'm always just like, you're not working on the homework, are you? Because don't even worry about the homework yet. Okay, good. All right. So then, so as we look here, our equation is going to be that distance divided by time. Okay. Now, again, capital R in this version of the book. The previous version of their book, they used S. And then, like I said, also you'll probably see it in other places, most often as lowercase d. Now, when we look at velocity, velocity's units are going to be distance divided by time. So we're going to have things like feet per second, inches per second, meters per second, or kilometers per hour, miles per hour. So always distance, how much distance are we going to cover per unit of time. Then that means our displacement is going to be in like a distance units, which will be anything from inches to feet, meters, centimeters, whatever it is that we're working with. And then time, seconds, minutes, and or hours is most common. Now, velocity is a vector, okay? Velocity is a vector. And as we talked about vectors in the previous section here, a vector is going to be represented by a line with an arrowhead. And we also know that it takes two quantities to fully define it, both magnitude, which is going to be the value of itself, and then the direction. So knowing, you know, by the arrowhead, if it's going left, right, up, down, but then also any angle other than vertical or horizontal. Okay, so to fully define it, we need both magnitude and direction. Now, the first type of motion we're going to be looking at is rectilinear or linear velocity. Okay, and as we look here, that familiar equation, v is equal to r divided by t, or like I said, distance d or s over t. And we're going to look at example 1, which is at the very top of page 124. So if I go underneath here, okay, you'll notice that in this example, we have a crate that's on a conveyor. And as we look at the conveyor, the crate is going to be moving to the left. And the problem statement lets us know that it's moving to the left at a rate of 25 feet every 40 seconds. And this is going at a constant velocity. And what they want us to do is they want us to put it in terms of velocity. So they want us to just take that distance and divide it by how much time it took to cover that distance so that we can get it into like a unit of time units. So like in feet per second in this case. So as we look at this problem and we look at, and I'm going to kind of cover this up because I know the equation is there and it's pretty straightforward, but I do want to show you some things using a simple problem on how I'm expecting the work to be handed in for the calculations that you will be doing for this particular module. So first of all, we have our crate moving on our conveyor belt, and we want to find the velocity. So first things first, we're going to identify v for velocity, the variable, and then we're going to write the equation in variable form. Okay, in variable form. Before you put any numbers or anything into it, I want to know what is the equation that you're going to use to solve this problem. So in this case, it's going to be velocity is equal to distance divided by time, or like I said, they use capital R divided by time, which I just think is an odd variable, but that's fine. Now, once we do that and we have our equation in variable form, now we can put the numbers with the units in place. So as you work your problems, I always want to see the numbers and I want to see all the units in every phase of the problem. You'll be writing this out for me, okay? So that we can do cancellations or combining where necessary, okay? So you'll notice that it says in here that we are going to be, our time is going to be 40 seconds and the distance is going to be 25 feet. So then we would take it, we could either, you know, go directly to the right of this and say 25 feet is our distance divided by 40 seconds. So notice that I have the units before I even start doing any of my, you know, division here. Then I'm going to do my math. I'm going to take 25 divided by 40. And I think that's 0.625. So then I'm going to put my answer as 0.625. And then I'm going to put my units directly next to it. Okay. Now, if there was any cancellation here of units, then I would do that in the top portion here. But this time there wasn't anything that I needed to cancel top or bottom. Okay. Once I have my final answer, I'm going to put a box around it. So this is like answering the actual problem or the question asked in the problem. Now, notice a couple things. Okay. First of all, I have the equation in variable form first. Then I'm going to put my values from my problem with the units. And then I'm going to do the math. And notice that as a final answer, I'm saying what the number is. Please do not put just 0.625 feet per second and put a box around it and say, that's my final answer. Give it the variable. So if we're solving for V, for instance, in this case, what is the velocity? Then carry that variable down and say V is equal to, and then the final answer. Okay, like make it definitive. So, so this is the format. So when I say show your work, this is what I'm looking for. Okay, all right. Any questions about that? Now, the other part of this that they're doing here is they're actually doing, and it wasn't asked in the question to do this, but they are doing a conversion here. So I wanted to kind of show you the way that, you know, I do conversions, or way I want you guys to do your conversions in the problems that we do. There are a lot of calculators out there online that, let's say you want to go from feet to inches. I know that one's pretty easy, but it might say multiply by 12 or multiply by, and it's a decimal value, or divide by, and then you just like magically have your answer at the end. But what I want you to do is I want you to do what I believe is called the ratio method. Okay. And you've probably seen this along the way, but it's a way that you can, I say multiply across the top, divide by the bottom, but you see the cancellation. And this way, there's never a question if you're going to multiply by something or divide by something or whatever it might be. So if I have my 0.625 feet per second, and I want to convert that to inches per second, what I'm going to do is, and again, I use vertical lines here, vertical straight lines, rather than parentheses, because this is a method that I learned quite some time ago. And what I like about it is when I have these types of, if you would, parentheses where they're straight lines instead of the curved, it signifies that I'm doing a unit conversion here. Okay. And it's not something that's part of the equation, or there aren't any other parts of, or any variables that I'm multiplying by. So I'll always use these vertical lines for my conversions. So if I want to change feet to inches, what I'm going to do here is, how this is set up is everything is on top. I'm going to multiply across the top, divide by the bottom. So that requires me to put my units in what I call up-down fractional mode. So you can't put feet and then a slash per second. You have to go feet on top in the numerator and seconds in the bottom in the denominator. So now I've got a, you know, and then this whole number, or the 0.625, is, if you would, over 1, as we learned in algebra. Okay. So now as I go across here, in this part right here, I'm going to put my conversion. So if feet is on top here, I'm going to put feet on the bottom, and I want to convert it to inches, and I'm going to put it on top. And all I'm going to do is I'm going to put now my conversion there. I know that there are 12 inches is equal to 1 foot. And now when I multiply across the top here, divide by the bottom, my feet are going to cancel out. So you would show those canceled out. And what's not canceled out is the inches on top, and then it would be per second. And that's what I'm looking to convert to. If I needed to do another conversion, you know, to maybe convert seconds to minutes or hours or whatever it might be, I would do that next conversion right next to it. Okay. But this is where I wanted to be, was inches per second. So now I'm going to simply multiply 0.625 times 12, and then divide by 1. And then I would have whatever my answer is. And my units this time would be in inches per second. Okay. How many have seen this type of conversions before? And again, I think it's called the ratio method. I'm not exactly sure. You've seen that along the way somewhere, somehow. That's the way I want to see it. That's all I'm going to say. It's the best way to do it. There's no question you know, you see the cancellations. You're not, you know, wondering, should that number be larger or smaller, you know, that kind of thing. So, so do them even for the easy ones. I want to see them. Okay. So yeah, so this would be an example of what I would want to see work-wise. Additionally, it has to be neat so that I can read it. I'm going to tell you, I don't spend time trying to decipher if it's a 5 or if it's an S, or if, you know, if somebody has to come up to me and say, no, see, I've got it right here. No. You got to be able to, and I'm not looking for perfection. I don't claim, I think I have decent handwriting, but I don't have perfect handwriting. Okay. And I'm not looking for perfection, and I do let things go, but an expectation of you out in industry is that you can communicate. And part of that is you have to document calculations that you do. So, so make sure that you're doing them in a nice, orderly way. You don't have to do these in CAD for me. You don't have to do them, you know, word process. Just take your time writing them. That's it. Okay. That's what I'm looking for. Okay. So, so that's just kind of, you know, looking at a simple problem, looking at velocity, and kind of getting used to what I'd be expecting for handing work in. Cause I know this is early on. You haven't had me for classes before, so I want to make sure that you have a good idea of what my expectations are. Pretty much however I show it, that's what I'm looking for. Okay. So let's look at velocity of a general point. So if we go to just a little bit lower on page 124, we're going to be looking at figure 6.2. There are 2 points, points A and B, that are on a link that is rotating around a fixed point, which is you know, by the frame here, or attached to the frame, if you would. And we're going to find out that there are some velocities associated with those points. So we're going to be looking at those. Now, we're also going to notice that points that are further from the pivot or the center of rotation, those points are going to be moving faster proportionally than the points that are closer to the center of rotation. Okay. So if we look underneath our camera, and here is the illustration I'm referring to. So on page 124, figure 6.2, we're looking at just a link. It's rotating about a fixed center, which is right here attached to what would be our frame symbol. And you'll notice that it's not attached to anything else. So we're just simply looking at a simple link that is free to rotate around that point. And along that link, there are 2 points. There's point A and there's point B. And each of those points you're going to notice have vectors, velocity vectors coming from them. The top one up here is identified as vector B, and then the one that's lower is vector A, or velocity A. Now, as we look at each one of those points, notice that the length of vector A is shorter than the length of vector B. And that's because of what we just said. The further we get away from the center of rotation, there's a proportional relationship, and the maximum velocity is going to occur out at the furthest point away, and then gradually get less and less as we move towards that center of rotation. Okay. Now, in the handout that I gave you, we see this on the very first page. So what we're going to do is we're going to start looking at that handout, because the book is I think a little light on this subject, which is the fundamentals of what we need to know to really kind of be able to solve these types of velocity problems, where we're looking at rotating links and such, and how they're related to straight line velocities. So I created this handout so that we can work through it and kind of make sure that we've got a good understanding. So you're going to notice after the first page, there's going to be some places where we can fill some work in, but I wanted to go over the first page first to get down kind of the basics. So we already talked about linear velocity, but down here where it starts looking at velocities on a single rotating link. So here's a single rotating link, and it's going to be rotating about point A. And we have identified on here 3 points, X, Y, and Z. Okay, and they're at different distances along that link number 2. Now, what you're going to notice here is that link number 2 is rotating, okay, rotating. And that's what that W2 is. That signifies what we call angular velocity, sometimes referred to as rotational velocity, angular velocity. And it's always going to have this W, which is I believe it's lowercase omega. And then it's sub 2 because it's the rotational speed or the angular velocity of link number 2 as a whole. Now, all of the points on link number 2 are all rotating at that very same angular velocity. So if this is going around, for instance, in a clockwise direction at 100 RPMs, that means that every point along there, X, Y, Z, the entire link, everything has an angular velocity of 100 RPMs, okay? But now the differentiator is as we move further away from the center of rotation, okay, from X to Y to Z, we're going to notice that our velocity, our straight line velocity vectors get longer. Now, straight line velocity, if this link is going around in a circle, each one of these points has a straight line velocity component. Do you guys remember that from physics, rotational physics? Yeah. So for instance, if I'm rotating on this link, right? Rotating on this link, and I suddenly stop and X, Y, and Z weren't officially affixed to that link, they would continue in a straight line, not in a curved path, right? not in a curved path, only because they are on that link do they go in a curved path. But if we would stop suddenly and they would be free to keep moving, this is that linear velocity that they're going to have. And again, the value, the magnitude of that linear velocity, how long it is or how short it is dependent on how far away from the center of rotation it is, okay? So the equation relating those three quantities is right down here. Straight line velocity is going to be equal to angular velocity times the radius of rotation, or the radius from the center of rotation that particular point is. So for instance, if I want to find the velocity of z, I would say the velocity of z is going to be equal to the rotational speed, or the angular velocity of link number 2. Remember, everything on that link has the same rotational speed, whether I'm out at the end or I'm close to the middle or close to the center of rotation. They all are going to be rotating at 100 RPMs, okay? And then it's gonna get greater and greater the further I am away from that center of rotation. So as r, or that radius, that distance increases, now my velocity is going to increase as well. And that's this relationship that we see here. Questions so far? Okay. Now, direction. Direction is really important. Direction of each one of these vectors is going to, number one, be pointing in the direction of rotation. So for instance, if I look at z here and I put my finger at A, notice that when I pull in the direction of that linear velocity component, it's going to rotate in that same direction that the entire link is, okay? So if I'm going, in this case, clockwise, then each one of these velocities are going to point down and to the right. You'll also notice the angle that they make with their radius of rotation. So for instance, this is the radius of rotation. This distance right here is the distance that x would be from its center of rotation. And you'll notice that there's a 90-degree angle there. Okay, so for velocities, our velocities will always be perpendicular to that radius of rotation. So y, it's perpendicular to this line, and then z is perpendicular to that one. If we go back to our book, even though A and B are on the very same link, notice that their radius of rotation is at a different angle. So A is perpendicular to its radius of rotation, B is perpendicular to it. So even though they're on the same link, they can be going at different angles because of their radius back to the center of rotation might be on a different line, okay? All right. All right, let's turn the page. Let's turn the page. Now, here's where we're going to start filling in some blanks, okay? Now, a big deal with me is that I always want to make sure you guys are like very hypersensitive of units. It's going to be your confirmation that things are set up appropriately. So number one, we want to know the expected units that we have for something. And number two, as we put them in problems, we're going to be carrying them through, and we're going to be sure that we combine and cancel where necessary. Okay. And then if we end up with the right units, we know, and it's a confirmation that our setup was good. Okay. So, so as we look here on the top, as we look at straight line velocity, what type of units would we be expecting for straight line velocity? Anyone? Meters per second. Yes. What else? Feet per second. What else? Miles per hour. What else? Kilometers per hour. Yes. So anything that is distance over time is going to be a valid units for straight line velocity. So as we're here, I'm going to use inches per second just for this example, and we'll kind of use those as we go down. So our radius, that's a distance, right? So what would we be looking for here? Inches, feet, meters, millimeters, centimeters, kilometers, right? Anything that is distance related or relative to what we're looking at. Now, angular velocity. I love that you guys are saying that already. Yes, radians per second, but what else? There's two of them, and RPMs, right? So I'm gonna put I'll put radians per second here, but then we'll also put another one. We'll put revolutions per minute. I always expand it out. Yes, you can write it as RPMs or it'll be given to us as RPMs, but when we're using it in problems and, you know, expecting to do either conversions on it or when we're looking at, you know, putting it into an equation and combining it, always expand it out so that you can see. Otherwise, RPMs won't cancel if you would. Okay, so now let's say that we're interested in determining what the angular velocity of something is, knowing the velocity and the radius. And this is simply a rearrangement of the previous equation. So here was the original, if you would, the base equation, V is equal to WR. So just using algebra and rearranging this, now solving for the angular velocity. We want to put the units in the top in the numerator for velocity. So we'll put inches per second on top. And in the bottom, we're going to put inches. Okay. So now when we cancel, now not worrying about numbers here, just looking at units. And that's why there's brackets instead of like parentheses. So if we cancel out our inches top to bottom here, we're only left with per second, like nothing per second, right? But in a rotational world, what are we really left with? You'll notice radians per second. Do you see how that comes out? So this is my little silly little thing that I've said for years. So I like to say that radians are kind of like Lucky Charms. Okay, they probably aren't magically delicious, but they do magically disappear and they magically appear. Okay, so when you end up with nothing per second, for instance, that's when radians magically appear. But if radians ends up being multiplied by something else, it'll disappear. So for instance, if radians is multiplied by inches and you're in radians per second times inches, well, now it's going to be inches per second, right? Because the radians just magically drop out or magically disappear. Okay. So, so just kind of a way to kind of remember that. But in and out of this equation, we have to have radians for the angular velocity. Okay, so if we will be given, all of our problems will give angular velocity for a link if it's part of what is the starting information. It'll always be in revolutions per minute, but we have to then change it to radians per second before we plug it into that equation. Okay, and that's going to be what we do down here. So let's practice converting from RPMs to radians and then from radians per second to RPMs. So the first one that we have here is we want to convert 500 RPMs to radians per second. So first things first, when we look at RPMs, we want to expand it out and put revolutions on top and then minutes on the bottom, okay? And then using that ratio method, we're going to fill in the boxes here. So the first one that we're going to do, I always tend to start on my top. If I know I want to change revolutions to radians, I'm going to then in my first spot here, put my revolutions on the bottom and radians on top. And then I'm gonna put the conversion. I know that there is for every one revolution, there's 2 pi radians. Okay. And that's the ratio for this particular conversion. So as I multiply across the top here and I divide by the bottom, do you see how my revolutions cancel out? Okay. So right now I'm in radians per minute. Do you see that? Because minutes are still on the bottom there. So I want to get this into radians per second. So now I'm going to deal with my minute. Since my minute is on the bottom here, I'm going to put it so that it cancels out on the top here. And then I want to convert it to seconds. So then I'm going to put my conversion in here. I know that there's 60 seconds in 1 minute. So 60 goes on the bottom here. And then my minutes are going to cancel because I'm going to multiply across the top, divide by the bottom. And I love that I've got calculators out already. What's my number here when I do exactly that? How many radians per second? 52.36. Anybody else get that confirmed? It sounds good. All right, cool. So hopefully, does that look familiar to you guys, doing conversions like this back and forth? Yep, there's calculators online that are going to be like, if you want to say, oh, if I want to convert from radians per minute to, or I'm sorry, revolutions per minute to radians per second, multiply by this number. Ugh. All right. What was that? Do you? Good. Now you get to do it this way. I find that I used to, when I was at the other college, I also taught physics as well. And that physics class, there was a number of different disciplines in there. So other engineering types were in there too, besides mechanical design. And I would always get the eye roll when I would explain this and how they had to write out their answers and stuff like that, because on those other disciplines, they had different teachers than me. They only had me for physics. They're like, well, we don't have to do this for any of our other instructors. And they weren't happy. They were like, wow, it takes so much longer. Okay, fine. But they had to do it if they wanted the points. That's how I graded. So I wasn't just looking at the final answer. I was looking at the whole process, and they had to follow my process. And by the time we got about 3/4 of the way through what would, at that time, it was semesters up there. All of a sudden, I've got those same students asking me, can you show me how to do the units for this problem? All of a sudden they were like interested in units. And then I was also getting comments that when they were doing the same unit conversion in their other electricity classes, all of a sudden they were like, it makes so much more sense when I do this. I'm like, I know. Units are huge. Units will confirm for you that you have everything set up, and setup is everything in a problem. It's everything. So yeah, I'm going to have you guys write this out for me, because it is going to give you a level of confidence that as you use this, we know we always have problems that it's multi-stepped. And if something goes wrong right in the beginning, everything else is bad. Okay. So take your time, write it out. Units are a big deal, and we'll always spend time on units. Any questions that you have on that, I'm happy to go over that. The next section here, we're going to be looking at radians per second to revolutions per minute. So go ahead and do the conversions here, and then see if we get the same answers. I'll let you fill it in this time yourself. You get 95.5. Did I do that right? Same thing or no? No, I didn't think that was right. What did I do wrong? 1060 times, what did you guys get? I got the same answer 3 times now. Did anybody else get 95.5?
I did.
You did? Okay. Yep. So remember, you're going multiplying across the top, dividing by the bottom. So 10 times 60 divided by 2 divided by pi.
Yeah, I think originally did, since you do it on the calculator, I did 10 divided by 2 times pi.
Oh, okay. Okay.
Forget that the calculator likes to separate the two.
Yeah, I use a different type of calculator than you guys do. So I don't know. I never got one of those graphing ones, and then you would write out the equation. I have a reverse Polish notation one. Been using it forever. All right. Any questions on that part? Everybody get 95.5? Okay. Awesome. How about those who are online? You guys okay? You're good? Cool. All right. Awesome. All right, let's turn the page. Let's do a couple examples here. So we're going to determine the straight line velocity of point B, that as it rotates on this link or this line at 100 RPM counterclockwise, 100 RPMs counterclockwise. So we want to kind of put our information on here first, as far as like what's here and what's not there. So first of all, this link is going in a counterclockwise direction. So this is going to be our W2. That's going to be our angular velocity of that link. So the entire link is going to be rotating counterclockwise. And we want to determine what is the straight line velocity of B, which is, we want to know what is VB, right? What is that? We're going to calculate that. Okay. So we need to draw VB on our diagram. All right. Now to draw VB on our diagram, we know a couple things about velocities, don't we? We know that the direction of the velocity is going to point in a straight line in the direction of rotation and perpendicular to the radius of rotation. So go ahead and draw VB on the endpoints of link number 2. Okay. As you're drawing it, what's your thoughts? Up and to the left or down and to the right? Up and to the left, exactly. Yes, you got it. So up and to the left, and it's going to be perpendicular to that line, going back to the center of rotation, and then we're going to label this VB. To confirm, right, we can put our finger at the center of rotation and pull in that direction, which matches the direction of rotation here. Okay, good, 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 good. So we want to determine, we want to know what the magnitude of that is. What is the number of VB? So what is my base equation that I'm going to use here to solve for the velocity of point B? You can look back if you need to. Yep, yep, exactly. And in this case, we're going to do velocity of B. It's the angular velocity of link number 2, and it's going to be the radius to point B. Okay. So write your equation in variable form first. Now we're going to put our numbers in. Angular velocity of B. So I'm going to put 100 RPMs here. And then I'm going to multiply it by 10 inches. Is that right? That's right. It's not correct. I cannot put my 100 RPM in this equation, right? Remember, this equation, I have to be in radians per second. So I'm going to erase this. I don't want to do that. I absolutely cannot do that. I need a different number, and my units need to be in radians per second, right? Radians per second. I'm sorry, say that one more time.
You just want it in seconds, or?
It's the most often used values. Yeah. So yeah, Adam's question was, could we leave it in radians per minute rather than always going to radians per second? It's kind of what the standard is, you know, so yeah. Yeah, this one isn't just because I like it that way. Other things might be, but not this one. This is just the common units that we use. So we want to go ahead and we want to do that conversion. So we're going to take 100 revolutions per minute, right? Up, down. And then we're going to say 1 revolution, 2 pi radians. And then we're going to do 1 minute, 60 seconds. Okay. And should get this in, cancel out, radians per second. As often as I've done this stuff, you would think I would have, like, I don't know, have an idea, and I still write them out because I'm a visual person. I think that's part of it too, right? You guys get 10.47. Okay. All right, so that's going to be our number. This is going to be our number then that we're going to plug in right there, okay? 10.47, and then we're going to multiply that by 10. So our velocity at B is going to be equal to 104.7 units. Radians per second times inches. What are my units for velocity? Oh, did you get a different number? Oh, you got it.
Went straight to adding the inches into my problem. Like I can.
Oh, you did it like right along it right here?
Yeah.
Okay, good. Yeah, you can totally do that. Gotcha. What would my units be here? So if I take radians per second times inches, what are the units for velocity? Inches per second, because what happens to the radians? Oh, come on, you can say it. They what? They don't just disappear. They magically disappear. They magically disappear. Okay, you guys aren't as amused by that as I am. It's okay. All right, and then we'll put a box around our final answer. And then we always are going to label it. Now, do you have to, in this case, we kind of, did at least I did my conversion down here, and I did my problem up here, just so that it's like easy to follow, if you would. If you need to number your steps, that's okay. I don't care. You don't have to like move in a linear fashion down the page, but as long as it's easy to follow and neat so that I can see what you did, I'm good.
You find the conversion in the same.
Yes, yes, I don't mind that at all. So what you're asking is, instead of having my 10 here, right? You would have had, for instance, you would have had 100 revolutions per minute, and then you would have done your conversions, right? And then had this in a parentheses, and then it would have been in radians per second, and then multiplied by your 10 inches out here, right? Totally fine. Yep, I like it. That's one reason that I use this convention, is so you can insert it, and you can see that that part of it is not variable driven. It's a conversion instead. Good. Any questions? These are fun, aren't they? Kind of fun. Let's go in the opposite direction. This one, on example number 2, it says determine the angular velocity of link number 2. In this case, knowing the velocity of B, right? The straight line velocity of B this time. So we want to find out what is the angular velocity. Now, as we look at the angular velocity and we create our arc, which way is the rotation? Is it clockwise or counterclockwise? Clockwise, right? We put our finger here, we pull in the direction of B, our angular velocity will go in that, in that same direction. So this is going to be my W2 this time. Good. Now, this time I want to solve for the angular velocity. So our base equation is going to be our W is equal to our V divided by R. It's just a rearrangement of our base equation from here. So this is going to be W2, VB, and RB. Then we're going to go ahead and plug in our values. Make sure you always put your equation in its variable form before you plug anything in. So this is going to be 250 inches per second divided by 15 inches. So canceling top to bottom, my inches are going to cancel. I'm going to have nothing per second, or what is it actually? Nope, not negative.
Oh, radians, sorry.
Radians. It's going to be whatever our number is, radians per second, right? It magically appears when there's nothing there. And what is the number that you guys get? Yep. Okay. Now, whenever we are solving for an angular velocity, or rotational speed is another way to say this, we don't leave our final answer as a radian per second. Okay. Mostly because, let's say we were going to size a motor for this, and we were going to say, I need a motor that is going to provide for me a rotational speed of 16.67 radians per second. That's when, when you talk to the person at the counter of the motor store. Or if you're searching online, are you going to find them in radians per second? Maybe. But what are the more common units that we want to put this into? Yeah, revolutions per minute. So always when you're doing a W for me at the end, if a problem is asking you to solve, don't leave it in radians per second. Convert it to RPMs. Okay. So we're going to take that 16.67 radians per second, and then we're going to convert it. 2 pi radians, 1 revolution. Okay, radians on the bottom this time, revolutions on top. And then we know that there's 60 seconds goes on top, 1 minute on the bottom. So we have revolutions per minute.
Now, I know that, it's technically, you know, spinning, but, do we want to go negative because it's clockwise,
Mm-mm.
or does that not matter?
No, not in this case. No. All right. Questions? Okay. All right. Our next example. This one's a really good example. I like this one. Here we have we have a link. It's like a triangle link, okay? And it is rotating about point A, which is attached to the frame, isn't moving, okay? So just this is moving. And it says that it's going to rotate at 15 RPMs clockwise, okay? So that means we're going like this, right? We're going to say W2 is equal to 15 RPMs, okay? And we want to determine the following. Okay. Go ahead and fill in what you can down below. Okay. Based on this information on top. I'll let you kind of fill in what you can. And if you're not sure, just skip over it. Okay. We'll talk about each one of these, but take a look. Okay, let's start just kind of discussing each one of these and, kind of talk about them. So starting at the very top, WA, or the angular velocity of A. What do you think that one is? Anyone else? Huh? It's the center of rotation, right? It's the center of rotation. So I think you could say that it's either 0 or just non-applicable, right? It's just the point that everything is rotating around. So I'm gonna put 0, okay? What about point B? What is the W of B? It is 15 RPMs because that is going to be on the link rotating at the 15 RPMs. So we can say 15 RPMs for WB. Angular velocity, WC. 15 RPMs, exactly. All of the points on that link are rotating at the same angular velocity of 15 RPMs. Good. What about W1? 1 is the frame. That one's 0 for sure. What about W2? 15 RPMs. Okay, yes, good. Oopsie, RPMs. Any questions on any of those 5, if you would? Good. Now let's look at straight line velocity component. What's the straight line velocity of point A? 0, correct. What is the straight line velocity of point C, or I mean B and C? You don't have to tell me the number right now, but did you draw it up on your diagram here? If you didn't, draw it up on the diagram. How would you show velocity of B and the velocity of C before we even worry about the number? How would you show it here? So you would show B kind of going down into the right, right? It's going to rotate in this direction, and then C is going to go up and to the right, BC, perpendicular to its radius back to the center of rotation, right? So that's going to be what it looks like. And you always want to put those on your diagram so you can see them, okay? And label. Now, calculating it. What's the equation relating the straight line velocity to angular velocity on a rotating link? What? W times R, yes, W times. I thought I heard a P in there. And I'm like, no, I don't think so. Okay, oops, W times R. W times R. Now, if I want to find out the velocity, I know I can't put my 15 RPMs in there, right? So I got to do my conversion first. And I'm going to do this twice. So I'm going to do it on the side. And then this radius is going to depend on if I'm at B or at C, right? So go ahead and, or do you guys know already? Do you know what your W is in radians per second? Anybody? Well, yeah. What's the number? What is it? 1.57 radians per second. Did anybody get that number? Yeah. Okay. Because then you have to multiply it 15 times whatever it is, right? And then this is going to depend on, my R is going to depend on if I'm a B or a C. So VB is going to be equal to W2 times RB, which is going to be 1.57 radians per second times this radius 4 inches back to the center of rotation. So my velocity at B, what did you guys get? 6.28. Yeah, sounds good. And that's going to be inches per second, right? Radians times inches. So here's that number 4 there. Okay. Any questions on that one? So then it's the very same process, except a different radius for C, right? So velocity of C this time is going to be that same W2, the 1.57 radians per second, times the R2 point C, the radius to point C. So 1.57 radians per second times 2.5 inches. We'll get it in there. So my velocity at C, what'd you guys get? Yep, 3.93, right? There we go. And that's gonna be that number. These are fun, aren't they? They're not bad. They're not bad. All right. Any questions on either one of those two? All right, cool. Velocity of link number 1, 0. Velocity, straight line velocity of link number 2. Depends on what? Where the point is. So if we look at link number 2, is there a straight line velocity of the actual link? No, because it's only rotating around. So we wouldn't even say 0. We would say it's really not applicable, right? It's not a thing. If you put 0, I would never mark that wrong, but you know what I mean? Like it's not a number. It's like, it's not a thing. What was that?
Where?
Exactly. Yeah. So if we're doing or if it's a different point somewhere else, then, right, we would have it associated with it. Good. So this is just kind of looking at all of them and seeing any questions on this at all. It's a nice little review. Okay. Got a little bit more to go. Things to remember. I want you to fill this in. With whatever you think you should put in there, okay? So the top part relates to straight line velocity V. The bottom part relates to angular velocity. So just put what you think. No right or wrong answers at this point, and then we'll discuss it and make sure you have everything that you need. All right, tell me, what are the equations for straight line velocity that we learned tonight, or that maybe even knew before? V is equal to distance divided by time. Yep, absolutely. And there's one more. Yep, exactly. So when it's rotating on a link, straight line velocity component is calculated using the angular velocity times its distance or radius from the center of rotation. Good. What are the units for straight line velocity? Meters per second. What else? It's per hour. Sure. What else?
Units over time.
Yeah, you could units over time. So you get it, right? You know. Awesome. Direction. What did you put for direction? Sure. little more than that. What was that? Sure. Yeah, but direction, like, how do we know? Like, when we put this here, what did we, it's perpendicular to its radius of rotation, right? And in the direction of rotation, those two things. So I think it's the very first page. It's this right here. The direction of the linear velocities is pointed in a straight line in the direction of rotation and always perpendicular to that radius of rotation. So this is exactly what it is. We always have to kind of, we have to know, right? And velocities are always perpendicular to something. So if you want to say perpendicular to radius in the direction of rotation, something like that. Okay. All right, angular velocity. What'd you put for this equation? Okay, V over R, good. Units. RPMs, what else? Yep, radians per second, awesome, yep. And then its direction. Exactly, clockwise or counterclockwise. Good. One last page. Any questions on here? Everybody got this? It's not. All right, one last page. Example 4 and example 5. On example 4, you want to draw the velocities, capital V or V straight line velocities for each of the links. Okay, and you're going to be doing them for point B on each one. Then on example number 5, you're going to draw the correct direction of the angular velocity based on the direction of the linear velocities of point B. Okay, so go ahead. Okay, as we look at example number 4, the one over to the left here, at B, am I going up and to the left or down and to the right? Down and to the right, perpendicular to the radius of rotation. You want to label that VB, goes like that. Next one, up and to the right, down and to the left. Up and to the right, perpendicular to, right? VB. And then the last one, left or right? Left, good. Perpendicular, VB. Any questions on that? Counterclockwise, clockwise. Clockwise, yes. Well, it's W2. We'll put 2 on here. There we go. Clockwise, counterclockwise. Okay. Clockwise, counterclockwise. Counter, right? Yeah. Okay. Now you know everything there is to know about velocities on rotating links, single rotating links. Okay. This is the first half of this chapter. If we go back to our PowerPoint presentation that we had, and we kind of go the rest of the way here, this is going to be a review of what we just looked at in that handout. Except, like I said, the book is a little light. They only do like 1 or 2 examples and they're done. And I want it, this is really important for what's coming next. So, so if you wanted to go through these, you can, but it's the very same information, just more. Okay. Some conversions as well. So, so that takes us to the end of what I wanted to cover tonight. Okay. That's as far as we're going to go in velocities, this week. And as we look back at our learning plan, okay, There is going to be a second, I'm just putting the finishing touches on the PowerPoint, which is going to be part 2, which is going to continue in the chapter. And this is where we're going to be looking then at putting the links together for bar mechanism. And we're going to be finding then velocities of those different links. Okay. And we're going to be using a method called relative velocity method to do that. And that's what we're going to work on the next couple times that we're together starting next week. Okay. So that's all that I've got for tonight. All right. So I am going to stop recording.